Want to start weather that's really you're used to seeing, things you see every day. Beautiful sunshine, clouds, rain come in, snow falls, wind picks up. We've learned all about the different variables and we learned about the planet as a whole, general weather system. So now we're going to pick up, basically in your neighborhood a little bit more. So, so what types of systems shape the weather at this latitude? Well, Daniel Defoe was the first one to say, hey, storms generally track from the west to east. And Ben Franklin argued that winds don't mean where a storm's coming from. He was one of the first ones to discuss that as well. So it's interesting. Go our history a little bit. We're learning. One of the first storms, for example, way back in the late 1700s, was a hurricane that came into the Gulf of Mexico. There was a station, a military station at that time, that detected it, got some of the weather from it, and it was able to. It's all had southerly winds, so it assumed the storm was moving literally from the south. It turned out the storm was moving due east, but just where the location was, so that areas that didn't know about the storm, because they assumed it was moving to the north instead of the east, never were prepared for it. We've come a long, long way since then, and we keep moving further in our knowledge. So most of the weather originates because we have different temperatures and different humidities. This is just a quick example of where different air masses come from that impact us. This past winter, we had several Arctic air masses seem to come right in a row. Uh, right now, I have a continental polar over my house. The temperatures yesterday afternoon were 73, 74. Right now, it's in the low 40s. And last evening, when the front went through, the temperature dropped from 73 to 59. And during that time, I happened to be going to a grandson soccer game. So it got quite cold and very windy. Winds gust over 35 mile an hour at our house at that time. Now, other very nice air masses could be a continental tropical air mass. It moves into the desert southwest and the Midwest sometimes. It's fairly dry and quite warm. You can get temperatures in Oklahoma and Texas well over 100 degrees in this kind of an air mass. Other air masses are maritime tropical air masses. A lot of them come out of the Gulf of Mexico or the southern Atlantic. If you lived on the west coast, they would be coming out of the tropical Pacific. Maritime polar. It's air that forms over the ocean, so it's kind of moist, but kind of cool at the same time. Think about it. If you were in Northern California and went swimming in the ocean, the temperatures are relatively cold, usually. That's a breeding ground for a maritime polar air mass. Moist, cool, not as cold as continental or Arctic, but cold enough that it can mess up a good day. So these air masses will modify as they move out of their area. They'll change due to the amount of heating coming from the sun, uh, different aspects to them. Maybe they'll move over water, a continental air mass will, so it begins to moisten. Tropical air masses don't modify as much. Think about this. They form over the tropical oceans, mainly. So they're forming over an area that doesn't really change a whole lot in temperature, maybe 2, 5 degrees or whatever. And yet, the air masses that form over Canada, well, in the winter, it could be minus 30 degrees. Up there in the summer, it could be 65, 70 degrees. That's a huge difference. Okay, fronts divide these air masses. And along those fronts where I would call interesting weather occurs, but people might not. Uh, there's going to be a change in density from between the air masses and all, and it is going to make a difference. And fronts aren't instantaneous. In other words, oh, 1 foot is one weather and 1 foot's another weather. No, they're usually stretched out and change over several hundred miles. The leading edge of that front may be at one point, but the real ending to that front may be 100 miles back. So we're going to look at a couple fronts. One, we'll just start out with a stationary front. It's a front that doesn't move. It's a very simple definition. And we've had several of those around as well lately, where they set up literally between my house and your all's last week, where places in West Virginia, Ohio, Pennsylvania were on the cold side of the front. I was on the warm side. It just stayed there. Waves would ripple along it, but that front would just bow up and down a little bit, but not change much. Very stationary. So, interestingly, warm air is less dense than cold air, so the warm air is always going to be rising up over cold air. So in this case, you can see the warm air lifting up slowly, and way, way, way out ahead of that warm front, you can start seeing cirrus clouds. If you were driving towards that warm front, those cirrus clouds would be thickening. They become allostratus clouds, and eventually nimbostratus and precipitation probably as you approach that stationary front. Get on the other side of the front, whole different, much nicer weather probably. Here's a warm front. The only difference is now the warm air is moving. So maybe you're getting snow at the beginning of this event. The warm front approaches you. That snow probably changes to rain or even freezing rain, and then eventually all rain as the warm front passes. And in the warm air, maybe you're going to get some showers or thunderstorms sometimes. There's a lot of moisture many times in these maritime tropical air masses. Colder air is always more dense. So when a cold front moves, the air is significantly more dense. It pushes a steeper slope, so you wind up getting the air as it's moving along, rising faster. You get heavier precipitation. Many times you'll get the thunderstorms along these fronts. Fronts don't always move from west to east. Every once in a while, they'll come out of the north and move down along the oceans. It happens in California. You can see a front start out up to the north over Washington State and just drop down along the coastline in California. What happens in the eastern United States, what we call a backdoor front. What happens many times is high pressure builds over eastern Canada. That cold air gets so dense it begins to push south along the edge of the eastern United States. And instead of moving towards the east, it's moving due south or even set of southwest. And it'll eventually pop up against the mountains, the Appalachian Mountains, and stall many times. So you wind up getting air coming in off the northern Atlantic, maritime polar air mass, cool, wet, moist, causes a lot of clouds. We get many of these in the springtime when the ocean is still cool. So we're going to talk about occluded fronts now. As a extratropical cyclone develops, it's going to have temperature contrast along it. And as part of that, there's a warm front usually at one section, probably to the northeast. We know in the southeastern section, many of you got asked the question, what kind of advection occurs there? Well, that's typically warm advection. The northwest section or north or even west section many times is cold advection. So we have a cold front to the moving down one area as the low forms, probably almost due south of that low. We have a cold front probably almost due east of that low. With time, as that low develops, the cold front actually is moving probably faster than the warm front. And then when it overtakes that warm front, what happens is the air that was ahead of the warm front and the air that was behind the cold front are now forming a front. The warm air that was between them is now all pushed aloft. And that's where we get the cold occlusions and the warm occlusions. All we're saying there is a cold occlusion means that that cold air that's come in behind the cold front is colder than the air that was ahead of the warm front. Warm occlusions, just the opposite. And you'll notice here all the warm air that went lifted aloft over that. Warm air is less dense than either of these cold air masses. This only happens near the end of the storm. So you look for occluded fronts as the storm's finishing up or getting close to the maximum intensity it's going to have. So clouds and precipitation develop along these fronts. Frontogenesis is when a front forms. So you get a low pressure system. What happens is counterclockwise winds around the low. You begin to push the cold air down, warm air is coming up, and you're getting a front because there's convergence right along that frontal boundary. Frontalysis happens when the winds diverge away from that front, making it weaker. Extratropical cyclones. Extratropical cyclones are not tropical cyclones. I have you discussing extratropical cyclones in your discussion this week. There are some out there, and they will probably continue to develop and change during the week. What I want you to not do is go back and find in history somewhere where a tropical storm hit land. That is not a extratropical cyclone. However, to confuse you a little bit, tropical cyclones can become extratropical. Extratropical cyclones. First, notice here in the picture, very beginning of it, we have a weak low pressure and a cold front and a warm front. Tropical storms do not have either one of those. So we have a batch of clouds with a cold front here. As the cold front strengthens, the upper levels get deeper. This is the upper level. They get colder aloft. And eventually, they get literally a circulation. The intensity gets more intense the further up in the atmosphere you go. So you wind up with some of the most intense circulation aloft. And right here in C is where you begin to see the occluded front. Notice at the beginning, they're very far apart, the warm and cold fronts. Cold front begins to catch up, and here it does. It's now pushing up that cold air that was behind it and pushing all that warm air up that was here. And when you, at the final stage, when you get really an occluded low, you get a very strong push of the warm air aloft. So this is the life cycle of an extratropical cyclone. These happen all the time. You have numerous ones pass your house during this winter. Matter of fact, all the wind you had the other week was caused by one of these as it went by to your north. And this is just a picture of it. You can see the comma shape right up here. And we want to understand why these clouds have comma shapes. That's where the conveyor belt model comes in. So let's look at a conveyor. What you'll find here is you have a warm conveyor belt coming up into the warm front. North of the low, you have what they call a cold conveyor belt. Usually develops at the mid-levels of the atmosphere and begins to push to the west. Remember, the circulation around the low is counterclockwise, so it's pulling this cold air to the west, lifting the warm air, but also it's lifting and rising as it's moving westward. The air is actually colder over here, so it's lifting, and then it hits the jet stream and curves back to the east. What you wind up with from that is a hook in the clouds out here, making it look like a big comma in the sky. That's how you get that shape at the end of the classic shape of an extratropical cyclone. Different quadrants, sectors of an extratropical cyclone have very different conditions. They all have the wind around them. And the stronger they are, the more wind. Remember, pressure gradient determines wind speed. Well, if you have a very strong low, like went by the other week, you'll get very strong pressure gradients. Now, you also have the cold air, which is north of the warm front, and to the west of the cold front, we have a warm sector. So if you're in the warm sector of that low, what are you getting? You're getting decent weather, warm weather, maybe a shower. Not bad. However, if that low is moving to the east and you're in this sector, this cold front is probably going to pass your house at some point. What you're going to get along that cold front is a pretty strong change of temperature and maybe even some thunderstorms. One of the ways to track the way a low is moving is how pressure is changing. Pressure will be dropping as the low is moving towards you and rising as the low is moving away from you. So one of the easiest ways to determine the motion of a low pressure system is see where the maximum pressure falls are and the maximum pressure rises are, and point right between the two, the center, and that is probably the way the low is going to move. You can see here there are a lot of principal low tracks. You're going to get the Alberta lows, which come by and impact the northern United States. They tend to move very quickly. Also, they don't tend to be as intense as the deeper ones coming out of Colorado or the Rocky Mountains, or even up along the East Coast that some of them do. Why are these more intense? Because you have very cold air that's moved south, warm air from the Gulf of Mexico, and the tropics to the south is coming up. You end up with much bigger temperature gradients. That makes them stronger. Also, if you want to know how much precip a low is going to have, see how close it is to a moisture source. Alberta lows going across the Great Lakes only get moisture from the Great Lakes. They don't get moisture from the Gulf of Mexico or the Atlantic Ocean, or even maybe just a tiny little bit. The Pacific is lost. Mountains are going to chew up all that moisture. So you only get a little bit of moisture with the Alberta lows. Colorado lows, right here, pulling a bunch of moisture up out of the Gulf of Mexico, lots of precip. So depending on what side of the low goes, and that is one of the challenges when you're forecasting weather. If instead of Chicago, if this was Charleston, West Virginia, for example, over here, if I am forecasting a low to come up east of you, I'm looking probably at in the wintertime, maybe a significant snowstorm, and winds will shift to the northwest after that as well. May stay all snow. If I am forecasting that same low to go up over West Virginia, this whole area then becomes rain. May start out as some snow, but likely becomes rain. Warm sector moves in, and you've got to wait for the low to go by before you start getting some snow on the backside of the low. So one of the keys, the further out in time, earlier I can detect where that low is going, the better chance I have of telling you exactly what your weather is going to be 2, 3, 4 days out in the future. Winter storms are part of an extratropical cyclone. They happen in the wintertime. They usually have either frozen precipitation, freezing precipitation, and blizzards are a subset of winter storms. We had one that impacted up in northern Michigan the other week. We've had some along the east coast of the United States. One of the key things is they got to last at least 3 hours with 35-mile-an-hour winds or greater, and the visibility has got to be less than a quarter mile. The only way that visibility is going to be that low is either very heavy snow or blowing snow. So you pretty much, speaking in general, with a windstorm like this, you're going to have very heavy snow and very strong winds. Here you see the typical winter storm coming out from Colorado. To the north of it, lots of snow, maybe freezing rain near the closer to the warm front, and eventually rain. And lines of thunderstorms. This is where you're getting your severe weather across the southeastern United States. That south of the low is in the warm sector. As that cold front passes, it causes a lot of lift. And remember, cold core cyclones are deeper aloft than they are at the surface. And here you can see a weaker one, not as strong, but it's still deeper aloft. The low is actually out in here somewhere. Warm core, they can be thermal lows like happen out in the desert southwest. We learned about the monsoon that occurs in the southwestern United States. That is formed from a thermal low. It becomes, because the thermal air is very hot, remember pressure changes slower in hot air as it's aloft, you wind up with high pressure aloft, so it's a weakening system in the height and may have low pressure at the surface, but it's all due to warm air. Anticyclones are just that. They are good weather, nice winds are coming, air is subsiding, you're getting divergence. You have very nice weather. It can be sunny and warm. It can be sunny and cold, but tend to have nice weather with them. They form wherever these air masses form, are typically where these anticyclones. So generally the winds around them, you know they're clockwise. And here we got the sea breezes. And that getting into the last part of mid-latitude weather. If you live in Ohio, you get a lake breeze. Live where I do, you get a sea breeze. What it is, the temperatures over the water tend to stay cooler. So over the land, temperatures are warmer. We know warm air tends to rise a little bit while you're pulling in the air from the ocean. The ocean arrives that way. It causes a circulation. They're going to be the strongest when there is the greatest temperature contrast between the water and the land. So springtime typically is the strongest sea breezes or lake breezes. In the fall, not as much. Valleys and mountains have breezes too, and they depend on where the sun shines. So a valley breeze have heating occurring on the mountain slopes, pulls the air up, drops down in the valley, so you wind up with the clouds on the side of the mountains and nothing over the valley. At nighttime, cold air starts to develop. We know about cold air drainage. It pulls down into the valley, gets colder in the valley. That's where your fog tends to develop. Chinook is just another form of a wind system. It happens in the Rocky Mountains more. All it is winds have been pushed in maybe from the Pacific, and they're wet, humid, and all of a sudden they get to the other side of the mountains. They're a little bit cold at the top of that mountain, so they're getting pulled down by gravity. The wind's blowing them down the slope. When they do that, we know that they warm, they compress, they get very warm and dry. They can be called snow eaters out in parts of the western United States. Santa Ana winds form. They're very similar to that, what we just saw there with the Chinook, except they'll form over the higher mountains to the west of western side of California, pulled down by gravity. If you have a pretty strong pressure gradient to add with it, you can get 75, 100-mile-an-hour winds coming down off the mountain. And we're at the mountaintop. They may be 60 degrees, even 50 degrees or so. When they're hitting the basin, they may be up to 90 degrees, but there's no moisture in them. Relative humidity around 2-3%. And here you can see the classic. You have low pressure down over Arizona, high pressure to the north. You wind up with a nice pressure gradient that's pushing down over the mountains. This is the powerful Santa Ana. It's what caused all the fires a couple years ago, these forms. So this is all about the mid-latitude weather. Hope you got a little bit out of it, and let me know if you have any questions.